Okay, good morning to everyone. I hope you're not feeling the fatigue of the school. We're starting today with Prahar last lecture, so please enjoy the last hour of this amazing lecture series. And of course, always feel free to ask questions also during the break.
Yes, thank you very much. Okay, so a long time ago, in my first lecture, I sort of rushed through it, but I essentially, hopefully, explained to you that you have to go through a lot of effort to do all sorts of renormalization of the charges, fields, masses, in order to derive this formula. But in any case, at the end of that hard work, which I didn't do on the board, but I hope that you guys can do it. I have in my notes, I have all the calculations detailed out, so you can look through that if you want. The endpoint of that calculation was essentially a formula like this. The idea was that for any endpoint function, if you have massless gauge fields in your theory, then the endpoint function factorizes into this e to the minus a, and then the rest of the amplitude, which is hard. And this a, we reduced it down to this integral, which we didn't compute or simplify any further. I'm going to do that today. And in particular, just based on dimensional analysis, at least, I showed you that in 4 dimensions this is logarithmically divergent, and it's perfectly finite in higher dimensions. But I'm not going to care about that distinction between 4 and higher dimensions today. The goal will be to reproduce that entire formula using symmetries, which is what I hopefully have done in the rest of the lectures. I've sort of laid the groundwork to show you what symmetries we should care about in this entire problem. And now that we have that, essentially what I'll be doing today is at most times just guessing and then checking, doing the calculation to check whether that's correct. It will be educated guesses based on stuff that we've learned in the lectures already today. Okay, so let's start. So the first 2 things I'll do is to show you that this celestial CFT has a U1 conserved current, and I'll construct that current for you, and a stress tensor, both of which I'll construct for you. Now immediately you should be confused because it goes against what I told you just yesterday, where I told you that every operator lives on the principal series, which looks like d over 2 plus I lambda, or plus I nu, whereas the stress tensor has dimension d, and a current has dimension d minus 1. So what's going on there? I don't know. This is an open question. We actually don't know what's going on there. We do know there's a stress tensor, but we also know there are operators on the principal series. And multiple resolutions have been proposed, but we don't really know which is the right one. It could be that in addition to principal series, you also have an extra set of operators with integer dimensions. I'll talk about the ones living on d and d minus 1, and Atul will talk about w1 plus infinity, which have dimensions 1, 0, minus 1, minus 2. So all infinite class of integer dimensions. So it might well be that in the full spectrum of the CCFT, you have to include the principal series plus all of these integer series as well. Or it might be that the way we should think about these stress tensors is that you do the celestial amplitudes and analytically continue in delta, and then somehow land on the stress tensor. It is true that the principal series forms a basis on the space of representations. So in principle, any representation can be always expanded in a basis of principal series. This is a fact from harmonic analysis in conformal field theories. You don't need to know the details. So it might well be that the operator that I'm constructing today is in fact like a composite operator built out of other operators on the principal series. We don't know what that is. We don't know which one of these is true. No one has ever answered that question. So I'm not going to even bother to try. The goal today is to just show you that such an operator exists because I'm going to construct it explicitly. What it means in the broader context of CCFTs, I don't have the answer to that. Okay, so I'm going to start not with the stress tensor, I'm going to start with the current, because as always, all the calculations that I'm going to do, I'm going to show you do the calculations explicitly, is much easier in the abelian photon case, but it's exactly the same in the graviton. We just have to deal with extra indices. So that'll be exercise for you guys. Okay, so how do you go about constructing a current? We do know there's a symmetry that exists. That's what I've told you all this time. There is a U1 symmetry, so there should be a current. Now, how would you go about constructing such a current? Well, you would use no other procedure. You know a symmetry, and you just use a no other procedure, construct a current. But we don't have the action. So I am going to give you an action, derive an action for you at the end of the lecture. Then once you have that action, you can use it to construct a current, and you will show that you reproduce just the current that I showed you.
How is it obvious that we have a U1 symmetry on the CCFT?
We have the large gate symmetry. The whole large gate symmetry is a symmetry, which we now know is definitely a symmetry of the CCFT, among which one of them is the global symmetry. And global symmetries have conserved currents associated to them. So there must be, for that reason we know there must be a current, so we would like to construct that current. We don't have the action, so we cannot use no other procedure. But we have something better. We have the Ward identity already, at least in some form, in the form of the soft photon theorem. And the Ward identity for a conserved symmetry, at least in standard CFTs, takes the following form. Takes the form right? So this is the Ward identity for a conserved current. But we know that the Ward identity for large gate symmetries is the soft theorem. So what we'll do is start with the soft theorem and try and manipulate it in some way so that I can reconstruct this formula. And once we do that, we would have constructed the current by figuring out how to manipulate the soft theorem into this formula here. Okay? That's the method. And then later, once I tell you what the action is, which I will also derive using symmetries, then you can go home and check that if I do the no other procedure on that action, you will also end up with the same current that I construct here. Okay, so let me again remind you what the soft theorem is, but now in this language of the celestial operators. So let me just say, I'm not strictly speaking, honestly just for convenience, though it can be done, strictly speaking, I'm not going to be working in the Mellin basis. I will just, all of these operators OI that show up in the rest of my talk will be the ones in momentum space. Just for simplicity, it's much easier to work in this basis for the calculations that I'm doing. Of course, you can always Mellin transform and get the statements in the other basis. Okay, so the soft theorem, if you remember, now let me, I'm going to write it out in this notation. So this is an n plus 1 point amplitude with a photon operator sitting in here. This A, remember, is the polarization, and this is in the limit. That's the Q. In the limit where Q goes to 0. Okay, with epsilon A. This is the polarization. This is the soft theorem. I hope you've seen it enough times now that you sort of remember. So what it is, let me now recast it into the form in these x, in these coordinates, at least label it in the right set of coordinates. So I'm going to do what I've been doing all this time. Q mu is going to be parametrized as this. And I'm going to similarly have a parameterization for pk, which might include massive. They might be massive, in which case you just add the mass term here and here. And epsilon A is 1 over omega. So you can almost obviously check that epsilon dot q is 0. This actually also satisfies a nice property that epsilon A dot epsilon B is delta AB. And of course, it also satisfies the polarization sum identity, which is epsilon mu A, epsilon mu B, plus terms that depend on Q. In fact, I can tell you what this is, where n is just a null vector. So this is some polarization, sum over A. So when you sum over all the polarizations, as we know, we get eta mu nu plus this stuff. All of this stuff, the exact structure of this stuff depends on the gauge. Of course, I've chosen a particular gauge to write this polarization, but maybe it wasn't impressed upon over here obviously the soft photon is gauge invariant, because if I replace epsilon with q, which is what you do to check gauge invariance, p dot q over p dot q is 1, and I just get sum over charges, which is 0 because of charge conservation. So obviously I can choose any gauge I want to recast this identity. Okay, and one last definition. Now let's define S of A is 1 over E limit omega goes to 0, omega OA. Right? This is the type of operator that we saw yesterday. Multiply by omega in order to get rid of this pole, and then take the omega goes to 0 limit in order to extract just this pole, so that this arrow becomes an equality. Okay, so you do all of that and you get SA of x, and I put in a 1 over E just to cancel this factor of E, which I don't like sitting around. This will give sum over k. I want to write it so I want to write it in the suggestive notation. Okay, hopefully this should be obvious, because this is, you take a derivative of the log, I get 1 over p dot q, that's this thing. Then you take the derivative of this, of course this pk doesn't depend on x, q depend on x, you get pk dot the derivative of q, but derivative of q is the polarization, so you get the numerator. Okay, so this is the structure of the soft theorem that I'm going to use, and now my goal is to do something to this equation. You see this side is almost already of more or less of this form. It looks very similar. You know, maybe if I was super lucky and if I just take a divergence of this side and I get a delta function, because I'm exceptionally lucky, then I would simply conclude that S is equal to J. This is what happens in 2 dimensions, actually, in 4 dimensions. So in 4 dimensions this question is really easy, but it doesn't happen in higher dimensions. So the question is, what do I have to do to this equation in order to reproduce the equation on the top? Okay, so as I said, we are going to guess our way through this, and honestly the simplest guess will be the right answer. Okay, so let's do some basic analysis. So I'm going to guide you through the guess, and then I'm going to ask you guys to guess, and then see if you land on the right guess. But let me guide you through it. Let's look at the quantum numbers of this SA from the CCFT point of view. What is the spin of SA? Maybe I call it J. What is the spin of S? It's a spin 1, it's just a vector. Okay. What's the spin of J, the current J? Also 1. Okay. What's the dimension of S? Well, we'll figure that out. What's the dimension of J? D minus 1. Okay. So, how do we figure out the dimension of S? The way we figure out the dimension of S is to remember that because here I'm working in the omega basis. In the omega basis, the delta operator, or rather D, I should say, D is minus omega del omega. And this S, remember, was defined so as to extract the 1 over omega pole. That's what it does. So if I take D and act on 1 over omega, what do I get? I get plus 1 times 1 over omega. It's telling me that the dimension of this operator S that I've constructed is 1. There's other ways for you to see this. The other way for you to see this is to start with, well, you look at D with S, this commutator, then you define this as a limit omega goes to 0 of omega of D with this, and we worked out what this was. We saw that this was like xa del A minus omega del omega O, and this part is always there for any operator, so this will always just be the identical structure, and I find minus omega square del omega O. So I just need to figure out how to take this limit. But this is easy. Remember, again, by definition, O of A is 1 over omega SA plus higher order stuff. So you take a derivative, you get minus 1 over omega squared. You multiply by minus omega squared, you get 1. You take the limit to 0, all of these higher order terms drop out, and I just get plus SA, which is how I read off that it has delta equal to 1. So anyway, any of these ways you can do this. Okay, now I suppose I've given you enough information to maybe just guess what the answer has to be. If anyone has seen a little bit of CFTs, maybe you can guess. Shadow transform. Okay, for those who don't know, let me now tell you what the shadow transform is. The shadow transform is a unique integral map which maps conformal primaries of dimension delta to and representation R under the rotation group to other conformal primaries also with representation R. Doesn't change the spin, but the dimension becomes D minus delta. And I can tell you what the transform is explicitly. So if I give you an operator O, which has dimension delta and some rotation indices as well, then the way you construct this is to this is the definition of the shadow transform, where I so in CFTs this sort of operator shows up quite a lot. It's called the conformally covariant stress tensor, not stress tensor, a conformally covariant tensor. This R is the representation of SOD under which this transforms. Though you have to be a bit careful because you see that determinant of I is actually minus 1. It is an orthogonal matrix, but it has determinant minus 1. So the argument over here is actually in OD. So in case this shadow transform is only defined for those representations which can be extended to of SOD, which can be extended to OD. Of course, of which the vector is 1. So you have to take the extension into OD, compute this representation, which will of course have the representation indices sigma prime, sigma, and anyway, so this is the definition. Importantly, it is not at all obvious. Well, of course, it's sort of obvious that this operator transforms correctly under translations, rotations, and scaling transformations. Basically, that's sort of clear. The one that's not at all obvious is special conformal transformations. So, exercise. Check that this thing transforms exactly like you expect under special conformal transformations. That is to say, k acting on this when x is 0 is equal to 0, which is what should happen. So check that. Okay, the shadow transform has a lot of nice properties. It has the property that shadow squared is proportional to the identity. It's some number, and you get back the original operator. And I'll tell you what this number is because it'll show up, well, basically just twice, but it's fun to know these formulas. So if I have a spin L representation, that is to say a symmetric traceless rank L tensor, of course the current is a spin 1 representation and the stress tensor will be a spin 2 representation. So in that case, this can be worked out to be some crazy formula, but it is what it is. That's the answer. This n delta basically shows up in sort of when you try to prove that this shadow transform is the square of the shadow transform is itself. Of course, as you notice, you'll square this, you'll get two integrals. One of those integrals has, in order for this to be true, one of those integrals has to reduce down to a delta function, right? Otherwise it wouldn't square. And indeed, the essential integral that you need to know in order to prove this, let's say z, x minus z, so that's a formula. When in your free time you can try to check whether that's true.
So are you always guaranteed that conformal primaries come in pairs, or sometimes you get 0 out of this?
No, you never get 0. Of course, that's not a local operator. You know, it looks like it's a local operator because it has x in argument x. But just because it transforms as a local operator that's not how you define a local operator. A local operator has to meet local operator product expansions. This operator, or whichever one in the lives in the CFT spectrum, is the local operator. It has local OPEs. When you do the shadow transform and construct a corresponding shadow operator, then obviously by construction that shadow operator will not have local OPEs, despite the fact that it looks like it has dependence on just a single x.
Does this not cause problems when you have like delta and d integers and delta large and d? Then n goes to 0.
No. As I said, it's not a local operator. The unitarity condition is on local conformal primary operators. So you can start with some delta very large, which is nice and local operator, and obviously you'll get a negative dimension operator on that side, but it's not a local operator, so it doesn't matter. It doesn't violate unitarity. Yeah.
Can you give me a reference for that formula, if you remember?
A lot of this is reviewed really nicely in David Simmons Duffin's and Peter Kravchuk's paper. What is it called? Light ray operators in a CFT or something like that. They have a very beautiful review in general. I really like that paper. You should look that up. Okay. Okay. So this was some aside into shadow transforms, and this will show up a lot. Okay. So again, it's totally fine to have delta violating unitarity bound because this is not a local operator. Just because it has x dependence does not make it a local operator. Just because it looks like one. For that you need to check OPE and whether singularities occur exactly where they're supposed to occur. That is the thing that distinguishes a local operator from a non-local operator. Okay, so, okay, this was just an aside into shadow transforms for those of you who don't know. But now that we know this, well, now it's very clear that this has to sort of somehow work out, we believe, right? So you take S. So notice what's happening when dimension d is equal to 2 in 4 dimensions. Then this is 1 and that's also 1. So in that case, that's the reason in 4 dimensions S was just equal to J. But in higher dimensions, you have to do this extra shadow transform. Okay, so what's the time? I was maybe planning, but maybe I won't. I won't do that. But it's explained in my notes. I don't have the time to go through this. Prove that if you do the shadow transform of the boxed formula, then take the divergence, you get exactly that. You will get exactly that when the operator OI is massless, because massless operators are local, like we saw yesterday. However, if they are massive, we saw massive operators are not local. So there must be, in that case, you end up getting, instead of delta k minus 1, you get the bulk to boundary propagator. Xk. So essentially this tells you that massive particles on the CCFT have a non-local charge distribution, and the non-local charge distribution is given by this function. Yes?
So SA was defined in terms of a local operator. Now we're going to do a shadow
From the bulk. The point, we are now trying to figure out what are the local operators on the CCFT.
to get local on the CFT.
No, not just by constructing it from the bulk, it doesn't necessarily mean it's local on the boundary.
But in the field theory, when you have a symmetry,
In ADS CFT, you do.
There's a field theory. You do not the procedure.
In field theories, you have to define beforehand what is your spectrum of local operators. Oftentimes, you define it by giving me a Lagrangian.
Fine.
In the Lagrangian, if you have a local Lagrangian, then whatever is appearing in that action will be local.
And the current will be local.
and then the current will be local. So right now on the CCFT side, we don't know which ones are local, which ones are not local. SA of x was built from bulk local operators. But whether they are local on the boundary, we don't yet know. And in fact, this suggests it's not, because we suspect or expect the current to be a local operator. And we are showing that the current itself is a shadow transform of S. So how can S be a local operator? So this strongly suggests that S is not local, but in fact J is local. Okay. Okay, I also won't go through this because it looks like this took more time than I thought. But let's now just quickly run through how we would do this for the stress tensor. What should be a starting point? Again, it's exactly analogous to all of this story. What's our starting point for the stress tensor? The subleading self-graviton theorem, which is related to Virasoro symmetries.
Why the subleading?
Because the leading is related to supertranslations, which is not diffeomorphism. Stress tensor is supposed to be the current corresponding to diffeomorphism. So we need to look for the corresponding soft theorem associated to Virasoro, which we briefly discussed was the subleading self-graviton theorem. So that's the operator that we should start with, right? But in fact, it's clear why we should have started with that for the other reason. So the graviton operator has two indices, symmetric and traceless. That's what defines the graviton. It's the symmetric traceless representation of the little group, SOD. So this has omega and x. So as we know, when you expand this operator in small omega, I'm going to get some 1 over omega NABX plus the order 1 term, which is the subleading soft graviton theorem, which I'm just going to call BAB of x. Right? This is responsible for the leading soft graviton theorem. It's the exact same Weinberg pole that we see over there, but in the gravity case, there's also a further subleading one, and in fact also a sub-subleading one. Okay, what's the spin of this operator? It's a spin 2 operator. I just told you. What's the dimension of this operator? 0, because it's the omega to the 0 piece. So if I shadow transform this, I'll get a spin 2 operator and a dimension D operator, D minus 0. Voila, stress tensor. Then you can check that this satisfies exactly the right word identity for a stress tensor.
Is it true that the only operator dimension D and spin 2 is stress tensor if the theory is not unitary?
No.
So
how do I know this? This doesn't prove that it's a stress tensor. You plug it into the soft theorem, you do the shadow transform, you take the divergence, and you show using that entire calculation that you get the right answer. As I said, the procedure I will take is guess, but then check. So this is the guess. This is how I motivate my guess that maybe it's a shadow transform. And now I have to go through some insane amount of calculations. These are not easy calculations. Maybe I should say this. Maybe I'll just write at least one explicit formula. So JA is, I've already told you, is the shadow transform. But there's a coefficient sitting in front, which is C1, 1. That's written up there. Maybe you see an immediate problem. What's the problem? 0. Yeah. So in fact, turns out that is 0, but the shadow transform is also 0. So what you actually have to do is do a delta. So remember, what's the definition of the shadow transform? The definition of this shadow transform is d dy I AB x minus y squared d minus delta, which is 1, times SB of y. So this is 0, but it turns out this is also 0. So you have to regulate, and the correct way to regulate is to take limit delta goes to 1, and you take this to be delta comma 1 just for spin. Remember, the second argument is spin. Spin is 1. And then this one you take d minus delta, so you compute this with arbitrary delta, then you have to take the limit delta goes to 1, everything becomes finite. And you get and then you show that this current. So this regulation process is necessary to do these calculations. This one is even more of a mess because the soft theorem is is really, really messy. Maybe I'll write the soft theorem just so you'll at least know once. I don't think I've written what I've ever told you what the soft theorem is. So the soft theorem in the case of the subleading soft graviton so this factor is a projection operator. This is killing off the 1 over omega pole. So this one, if I do 1 plus omega del omega, that gets rid of this piece right here. It kills this piece. Then I take omega to 0, which kills off all the higher order terms here. So this limit on the right hand side is precisely extracting this operator, which is the subleading guy. So in momentum notation, this was only even though there's a huge 50-year history of soft theorems, this soft theorem was only discovered in 2014 using these asymptotic symmetries. Basically, Andy, once we figured out that there's a connection, we showed that supertranslations is related to the leading soft theorem. The next question was, well, we already know superrotations exists. So what is the Ward identity for superrotations? And there must be a soft theorem associated with it. And that's how this was discovered. And then we told this to not me, but Andy went to Freddy Cacciazzo, a big name in the amplitudes community, and asked him to check whether such a soft theorem exists, and it does. With explicit calculation, then you can check that it actually does. So this is one of the nice things that comes out of this symmetry sort of interpretation. You can find new soft theorems by starting from new symmetries. And the reverse has also happened, by the way. There were soft theorems whose symmetry interpretations we didn't know, and now we've discovered new symmetries because of that. So this is epsilon AB. This is a graviton polarization. Pk mu, Q rho, let's put rho on top, J So as expected, you see the angular momentum tensor is showing up in the subleading soft theorem. And you can also check the gauge invariance of this quantity. Firstly, it's order 1 because there's a q in the numerator, but there's also in the denominator, but a q also in the numerator. So this is order 1. You can check gauge invariance in the usual way, and you can show that gauge invariance is the same thing as angular momentum conservation, as expected. So we clearly know that there's some relationship to angular momentum and rotations hidden inside of this soft theorem, and therefore it's not surprising that the stress tensor is constructed out of this. So now this was in momentum notation. If I instead recast everything into this x, using this momentum parametrization, you get some form that's really, really not appetizing. But I just want to write it out to show you that exactly the right set of structures that we expect in a S matrix void identity are showing up. In a stress tensor void identity are showing up. Where this monstrous tensor, sorry, just a minute, let me finish writing this. Okay, there's the full answer. Okay, so this equality over here is this insertion of BAB. Now what you have to do, take the shadow transform of this entire thing, this very crazy looking thing, that gives you the stress tensor. Then take the divergence to check that it gives you the Ward identity. Let me just show you that it's reasonable. We are all getting all the right set of terms. What is the stress tensor Ward? Maybe I should also write down for those who may not. The stress tensor Ward identity is very simple. It's del A TAB is sum over K delta x minus xk del xka plus del A delta x minus xk delta plus SAB del B of delta x minus xk, and some factor of I is playing around somewhere. This is the stress tensor Ward identity, and we have exactly the same structure here. There's a del xk over there, there's a del xk here. There's a delta over there, there's this minus omega del omega here. There is this SAB times derivative, there's a SAB right here. So it looks like it's going to work out. It's not. And the main goal is to check that all the factors of 2 and I and all of those things work out, which they do. Okay, now, questions? Now I'm going to construct the effective action for the soft modes. So I didn't make any notes, I'm just going to sort of try and just go through this paper and see if I can extract the appropriate parts, sections from this paper to explain how to do this. Of course, if I went a bit too fast, please ask questions, ask either now, discussion sessions, if you want me to go into technical details. Okay. Let's do the action. So what's our starting point? Remember, we want to compute a scattering amplitude, which we know in QFT is given using a path integral. So there's some integral over some set of fields e to the is, and then you insert these operators.
Are we assuming that we have a local integral?
This is a bulk thing, so of course we know how to. This is all bulk. So these are bulk fields. Okay. So as we did with the when we were working on deriving the infrared divergences, let's break up all of my fields such that when you have momentum k, which is less than lambda and mu, so call these the soft modes, and the hard modes have momentum greater than lambda. Okay, then I'm going to take this path integral, break it up into an integral over the soft modes and an integral over the hard modes. Then I'm going to integrate out the hard modes. Okay, when you integrate out the hard modes, you end up getting something that looks like integral over d phi s, just the leftover integral over the soft modes, some effective action for the soft modes, which is what I'm going to fix right now. I'm going to tell you what this, I'm going to figure out what this is, and there might be some interaction terms which tells us how these soft modes couple to the operators that I've inserted inside this particular S matrix, because when you integrate out the hard modes, you'll get some contributions from whatever these operators are. So you'll get some interaction term which tells us how phi of s interacts with what I'm just going to call a matter current, the current coming from whatever these operators are. And then of course the integral over the hard modes gives us precisely the hard scattering amplitudes, the A hard that I wrote over there. So this is precisely the type of factorization that we are after. All I need to prove is that this factor sitting in front is e to the minus a. Then I'll be done. If I can show that this is e to the minus a, this is just a full hard amplitude, I would have derived in the whole formula for infrared divergences. Okay, so let's go step by step. I need to tell you what is this. I need to tell you what is this. And I'm going to try to motivate what these structures must be, in some sense, using symmetries. Okay, fine. Let's now do this. Let's start with the kinetic term. So what are the soft fields? So the first question is, what are the degrees of freedom in the game? That's what we do. So essentially all I'm doing now is the standard type of chiral Lagrangian thing that you do in QFTs. The way you sort of write down the effective field theories for pions, you figure out what are the right degrees of freedom, then you just write down the most general action in sort of a derivative expansion that's consistent with symmetries, and then you take it from there. Then you fix the coefficients by matching it to experiment. You know, that's the sort of idea that we follow, and I'm going to just follow through with exactly that. The only guiding principle is symmetries. Okay, so what are the set of degrees of freedom? We already know this. We have spent a lot of time figuring out that there is this mode C, which is the boundary value of the gauge field. That's a two-dimensional mode. So remember what this was. This was A on the boundary is equal to del A of C. When we were deriving the symplectic form, this was one of the soft modes. And the other soft mode was, of course, N, was NA, which is integral of FUZ. This in particular is the soft photon mode. And for reasons that, despite the fact that I was the author on both the papers, we decided to change notations midway. In what I showed you on the board today, I instead defined the operator SA. And there's some factors of 4 pi or something between NA and SA. So I'm going to work with SA because that's what I have in this paper. But they are the same mode. They're just some overall factors of 4 pi, which I've not bothered to write down. And of course, SA itself, remember, just like NA, is a total derivative of S, which we saw because the soft theorem was del A of log. So insertions of SA is a total derivative times the log. So this S is precisely insertions of this gives us a log. As before, operators which have logarithmic terms in their OPs are not well defined, but they're still convenient to use to write down actions, because we can use it to construct exponential type operators, which we will do because they will play the role of dressings. Okay, so what we want to do now, so I'm going to do the following. I'm going to only talk about the infrared divergences. Remember, infrared divergences, we had all the external particles were hard, and the divergences were coming from internal loops. S is the operator that corresponds to external soft photons. So in order to derive that formula up there, I don't need to insert any S. So I can also integrate out S and have further effective action just for C, just for simplicity. So the way I'm going to proceed with this is find the effective action for C and then integrate in S later on, because I want to deal with one mode at a time. I don't want to do too much at the same time. Once I figure out the effective action for C, I'll put S back in, such that when you integrate it out, you get back the effective action for C. Okay, so the only thing I need to know is S effective for C. Okay, but the action has to be invariant under C of x goes to C of x plus lambda of x. What action can I write down that is invariant under this? Because this is the large gauge symmetries. So, okay, if this was not a function of x, what action could I write down? Anything that depends on the derivative of C. Okay, but now there's a lambda of x, so what can I write down? Nothing. Absolutely nothing. Because of course, if this is the symmetry, I can go to a frame where this sets this to 0. So I'm done. We can't write down anything. Let's go home. But, oh, I erased it. When we were breaking up the path integral into soft pieces and hard pieces, we introduced a scale by hand, mu, which explicitly breaks this symmetry. So now, because I have explicit symmetry breaking, I should be writing down terms in the action which explicitly breaks this symmetry. This is what you do also for instance, pions, which they're not actually massless. But you start off by writing pion Lagrangians which are shift symmetric, pi goes to pi plus c. and you write del pi squared, blah, 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 but then we know in nature that pions do actually have a mass, so you write down explicit symmetry breaking terms. So now by hand we have a scale in our problem which has explicitly broken these asymptotic symmetries because I've put an IR cutoff. You can no longer take the soft mode, the soft limit. So now my symmetry, what's the leftover symmetry? How much of the symmetry have I broken? I've broken everything except the constant mode. The constant mode is just U1 global charge symmetries, and we still have that symmetry. I haven't touched it. I haven't done anything to that. So now all I need to do is write down terms which are invariant under this, and whose coefficients will necessarily be proportional to the symmetry breaking parameter. In our case, mu. Okay. So again, I'm going to just write down the simplest action that works, and the simplest action. Let me just at the end, I'm going to fix this coefficient by matching it to that answer. So let me just keep it alpha for now, and we'll see later that it is exactly proportional to mu. That is showing up in that integral over there. So the simplest action is dd. Oh wait. So let me first write the simplest action and then tell you why this is wrong. Del A of C squared. This is the simplest action. It's just the kinetic term for C, which is invariant under C goes to C plus constant. Why is this potentially wrong? I have inherently made a second assumption, which is always correct in QFT, but is not necessarily correct here, and I have to be careful.
The sign? The sign?
No? I've said alpha is anything, so I'll fix that. If that's positive or negative or I, it doesn't matter. What else have I assumed in writing this action?
That actually is quadratic in shape.
Well, this is the lowest derivative term. Of course, there could in principle, that is local. Local. We know the bulk theory is local, we don't know about the boundary theory. The whole point is that we are trying to figure out whether the boundary theory is local, and if it is local, it's local in which variables. So I have inherently assumed that it's local. Now, at this point, you might just guess, why not, and say, well, maybe it is local, but in terms of the shadow transform. Not in terms of C. We've already seen, we have played around quite a lot to see that it looks like all the local objects in our theory, which should be interpreted as local stress tensor and current, are shadow transforms of bulk quantities. So of course C is a local from the bulk point of view, but we don't yet know whether it's local from the boundary point of view. So we might just guess at this point, since we're just doing that all the time, that the boundary action is local, but in terms of the shadow transform of C. But I'm not going to do that, because maybe you don't like so much guessing. Let's just write down the most general thing, but we'll find that that's actually the right answer. So let's just write the most general thing. The most general thing is alpha ddx ddy okay, done. So this is S, the effective action, the kinetic term. Let's look at S interacting, which, remember, the interaction includes C and whatever matter current that you might get from all the other charged matter fields.
What is PAD?
Anything. I'm going to fix it soon. The whole point is that I'm going to now take this as my effective action plus this, do the path integral over C, get some answer, compare it to that, and then try to find what P has to be so that the matching occurs. However, as I've already explained to you, this is just going to be the shadow transform for reasons that we have already guessed, but I don't want to, in order to not make so many guesses, to actually prove that this is the unique answer, I've taken the most general form. Okay, so what should I write down for this? So where is this interacting term coming from? So this is coming from the fact that when I have my hard operators, remember all of these operators O of x, they transform under large gauge transformations. Remember, this is something we worked out, that under large gauge transformations, this goes to e to the iq lambda of x O omega of x. This is for massless particles, and as I just showed you, for massive particles, it's not going to be this. It's going to be integral d dy kd m over omega yx lambda y. Yeah. As I said, massive particles have a non-local charge distribution, which is a function of this kd, and then you multiply by y, integrate over y. So this is a non-local charge distribution. Okay. So what I would like to do in order to figure out what this interaction term has to be is to take this omega of p, right, break it up into O soft, which depends just on the soft modes, C, and O hard, which these hard operators generate your hard amplitude. Okay. Okay, now I'm going to ask you to guess yet again.
Why can we do this split multiplication?
Well, we can do the split in the path integral. Yeah, why can we do the split? There is a reason. I forget now. So, okay, ask me a bit later. I'll have to think harder about it, but I want to finish. I think it's a very good question. I don't remember that off the top of my head. I should. It's obviously an important point. Okay, suppose such a factorization happens. Okay, what does this soft operator have to be in order to reproduce this transformation? How does C transform under large gauge transformations? E to the IQC. So this operator is simply e to the I q C of x, because we know under large gauge transformation C goes to C plus lambda. So when C goes to C plus lambda, we'll precisely pick out this phase. Yeah? So this interaction, this S int, well, remember I was writing e to the minus S int. So this e to the minus S int is simply e to the minus I sum over k qk C of xk. Now let me just, this is all massless. Let me just simplify for massless. Well, obviously everything generalizes to massive. You just have to include these non-local distributions. So S int is just this piece over here, sum over k. Sorry, did I forget something? No, this is fine. This is fine. This is fine. This is S int.
Symmetry, the constant is guaranteed by the sum of the charges, and everything is fine.
Yeah, exactly. When it goes, very good point. So obviously, this breaks that explicit symmetry, the lambda of x part. But when the global part is still completely a symmetry of this theory because of charge conservation. A good point. Okay, so now I just need to compute this path integral, e to the minus S effective of C minus S int of C, and now J, where I was calling J over here. Anyway, you know this is the J is whatever is involved with this Q. They have to put a delta function x minus xk. Well, I hope all of you know how to do this. It's a simple Gaussian path integral. There's really nothing to be done here. Complete the square and find the answer. And this path integral is equal to e to the minus 1/4 ddx well, just that, where I didn't tell you what the small j is, but when we were doing the shadow transforms for the, remember we had S of A, the soft theorem. This goes like this curly j, which is what I defined. So then JA, which is the shadow transform of SA, has an insertion which I was calling, which I didn't call it, but I'm going to now define it to be the small JA. Essentially, what is small JA? We already also know this. We know that del A, small j, capital JA, the insertion of this thing was precisely sum over qk, the delta function x minus xk. But this is exactly the object that's entering over here. I can rewrite this entire term as integral d dx qk delta x minus xk times c of x sum over k, and then this sum over k is integral dtx small ja and then integrate by parts ca of x. So it's very clear that this charge thing here is precisely this ja, because the divergence of that is precisely this delta function, and so then it shouldn't be surprising that this ja is then showing up when I do the Gaussian path integral, and it's showing up as a square. And last thing, now I need to convince you that this answer is the same as that integral, especially in the case when PAB is the shadow transform. In other words, it's IAB. That.
Why is not the inverse of PAB?
Yeah, it is the inverse of PAB. I put in my notes, this is P inverse, so that this P is the propagator. Okay. Just 2 more minutes, then I'll be done. I'm really sorry.
Actually, moving to 5 minutes.
Oh, okay. Where is this? Okay. Here. Okay. So let me manipulate that equation. So notice here, because S and J are related by shadow transform, so it's clear that JA is roughly the shadow transform of this curly J piece. I'm telling you that because it will show up over here. Okay, now let me manipulate that equation and bring it into a form that looks more like this, because this right now it just looks crazy. There's no way this is equal to that. Okay, so I need to perform the integral, which is madness, but let's do it. So there's a q mu in there, but that's an off-shell momentum. So off-shell, I need to now tell you how to parameterize off-shell momentum. And I'm going to off-shell momenta have a very simple parameterization. And so then that integral over d dk essentially becomes integral d dx integral d omega in R. Because now it's off shell, so there's no need for omega 0 to be positive or negative. It's supposed to integrate over everything. So now omega is R, and I need to put in this absolute value, and integral over R d kappa. So this is a full off shell integral. Okay, now let's look at the integrand. So let me first manipulate the integrand in a particularly nice way. So this thing over here is I put in a mu nu, and then there's a eta mu nu, but I'm going to replace the eta mu nu with the polarization sum, epsilon mu, epsilon a mu, epsilon a nu, which I can do, of course, up to gauge dependent terms, but the gauge dependent terms don't contribute because of charge conservation for exactly the same reason as always. So this piece, this term in the numerator actually becomes pk dot epsilon a pk prime dot epsilon. Let me maybe tell you where I'm going with this. I'm going to show you that this factor is the soft factor squared. So this factor is curly ja squared integrated over x. And because small j is just a shadow transform of this, if I choose PAB to be the shadow transform operator, then this will simply replace this j with a shadow transform, that with a shadow transform, and this full integral will reduce to the square of the shadow transform of j, but that's square of curly j. And I'm going to show that this entire integral reduces to square of curly j. Okay, so that's that. So let's look at the integrand. So the numerator is pk dot epsilon a, pk prime dot epsilon a. Now, same thing as before, you plug in all the momentum parameterizations that I've been telling you all this while into this entire formula, you get kappa plus I epsilon. Now the I epsilon prescriptions become really, really important. So these hatted ones are the ones without omega. I've removed omega everywhere. And I did say the I epsilon prescription is important, but I also haven't kept track of it here. The details are all in the paper. I'll tell you what the paper is at the end. It's my latest paper. Okay, so I'm going to solve the kappa integral first by contour integration. And it's going to be the usual way. So you have to sort of look at the I epsilon's signs everywhere and then figure out if I should close the contour up or down, depending on which sign there is. So for example, maybe I should have put this in here, plus I eta I j, and this is minus I eta j. Eta is the sign of kappa, because remember I have to integrate over, sorry, eta is the sign of omega, this omega over there, so the sign of the energy. So for example, let's just look at one quick example. If eta I is minus eta j is equal to minus eta, then what's the pole structure in kappa space? So there's one pole at kappa is minus I epsilon, so that's sitting over here. So if eta I is equal to eta, so that means this is a plus I epsilon plus some factor here, so then there's another pole there, and then this pole is also here. Did I get this right? Yeah, right, this is correct. So I get all three poles are in the bottom. I just close it on top and I get 0. Okay, and then you can just keep doing this for all possible pole structures. This is a standard IR divergence calculation in Weinberg you can find. And so anyway, that's definitely what you have to go through. Let's just look at one of the poles, just to see what the contribution looks like. So I want to look at another case actually. So let's see when eta is equal to eta j, and let's say this is equal to plus eta. So then this pole stays exactly in the same place here. When eta I is equal to eta, so there's this pole goes there, and now this pole goes up here. So now when I close it on the top, then I'm going to pick up one residue. Okay, and that's just going to evaluate to something that looks like pk dot epsilon pk prime dot q times pk dot q minus pk prime dot q. Now I can get rid of the I epsilons because they have served their purpose. Oh, notice that there is no dependence on omega anywhere here. Omega is gone. So actually I can just perform this integral. Oh, sorry. So this integral over omega is not from in R because I had these. The whole point was that I'm extracting only the contribution of the soft modes. So mu2. So this is only over the region where omega is lambda and mu. So this number is alpha. It's going to be the coefficient of this entire integral, and that coefficient of course shows up here and in the final answer for the Gaussian path integral. So we see that alpha indeed depends on mu and lambda, exactly as expected. Okay, so this is a mess of a calculation. Anyway, so this is one contribution from the pole. Then you need to look at all the other contributions, sum over all of them. A big mess. but the final answer is alpha times a1. So this factor a is a1 plus 2 pi I a2, and I'll just tell you what a1 is. I mean, I've already told you what that is. And there's some much more complicated formula for a2. Okay. Did I erase it? Well, okay. So the formula I had, the result of my path integral, the result I got by doing the path integral, which is what I would like to match with that, was alpha ddx ddy pab x minus y small j ax small j by, where this curly j shadow transform was the shadow transform of this thing. Of course, shadow transform square, so I can put this on either side. So it's now clear that if I choose p a x minus y to be integral dd z I a c x minus z over x minus z squared, and then another factor b c y minus z over x minus z squared d minus 1, then you see that this factor, when you integrate over x, this integral, this factor, and this j will give us a shadow transform. And then this integral over y, this factor, and this j will also give us a shadow transform. And then the final answer will be exactly that. Will be exactly this. I'll tell you about the imaginary part in a bit. We don't understand the imaginary part. Putting all of this together, we now know what the effective action looks like, and the effective action looks exactly like ddx cax shadow transform squared. So the action is local, but in the shadow transform variables. Seems to suggest, I would love to conclude, I don't know why I'm hesitant, but I want to conclude from this that indeed the correct set of local operators in the CCFT are shadow transforms of bulk local operators. So this is so let me stop here. The only thing I'll say, we don't know how to understand this A2. There is this amazing imaginary piece. I know the action. I can write it down, but I don't have any symmetry interpretation of that action. So this is not published work. I know what I need to write down in order to reproduce this term exactly from the CCFT side. But like I've shown you here, I'm not able to motivate it from any symmetries. I don't know why that's the action. I just know it works. But I can show you the exact form of that later if you're interested.
Is it the shadow transform of the derivative of C or derivative of shadow?
Derivative of C. You take the derivative first. After all, it's the derivative of C that's really appearing in the gauge field. There. So in other words, you can just take this to be the bulk gauge field itself, A of x on the boundary, then you shadow transform. Okay, so.
Derivative doesn't have any nice commutativity.
No. Okay, so let me conclude my lectures here then. To summarize, what I started off with was did some space-time analysis to derive the existence of certain symmetries. I showed that the Ward identities for these symmetries are the well-known soft theorems. Once we understood that's from the space-time structure, which is a bit constrained, we find it very hard to understand the space-time structure beyond 4 dimensions because of a lot of complications in the structure of space-time. However, we can go past that by moving to momentum space and then doing more in momentum space. What I did in momentum space then was to show you that there's a very nice conformal structure for scattering amplitudes, which when you do a Mellin transform looks exactly like correlation functions of conformal primaries. And I constructed the currents in 2 dimensions. By the way, these become Kac-Moody currents. There's a nice, amazing, enhanced holomorphic symmetry for all of these. Atul will tell us about some of those. We constructed the stress tensor, and I also constructed an effective action A. I didn't tell you how to include S, but you can integrate in S as well. But we have an effective action for all the soft modes, C and S. And when we compute the path integral with this effective action, you can reproduce the entirety of all the soft physics that we have studied, infrared divergences and soft theorems, everything. So I'll just stop there. Thank you very much for listening.
First of all, thanks, Prahar. That was really great.
Thank you.
Hope you guys enjoyed inside it. Question, yeah.
We can do it later.
Yeah, no, I was
Yeah.
saying that we slightly overrun.
Yeah, I'm
So
really sorry.
We have possibility of one quick question, or we can continue discussing during the break. We have today's discussion session as exercise, and also tomorrow after lunch. The entire afternoon is dedicated to just discussion and exercise. So
Yeah.
around until
Yeah, I'm around for the rest of the conference. I did go through a lot of the tedious calculations. I did not go through a lot of the tedious calculations, but if you look through the notes, there are exercises sprinkled all around the place where I've given hints for how to go through the calculations. If any of these, please go through them if you're interested, and if you can't, if you're interested but are unable to, ask me. I'll help you through them.
Okay.
All right, thank you.
Let's take Prahar again.
Yeah.
The shell transform on the right variable in the sense like in which you can think as a shell transform as like boundaries or boundary properties, like in EDS.
Yeah. There is a